To find the area between these two functions on the interval from -1 to +4, I graph them in Desmos. I notice that they intersect here at the point 1, 2, so that's this point right here. Again, to double check this, you could say, where does the function f of x equal the function g of x? It's two linear equations, that's where x plus 1 is equal to 2x. If we subtract x from both sides, we get 1 is equal to x, and okay, that makes sense. This is the point 1 where they intersect. In terms of using our formula for finding the area between two functions, it was the integral from a to b of f of x minus g of x. But this only works if the function f is always greater than the function g. And that is not the case on this interval if we go from -1 to +4. It switches. From here to here, the function f is greater than the function g, but then from here to here, the function g is greater than the function f. To find the area, we have to break this up into two separate definite integrals. So one's going to be the integral from -1 to +1, and it's going to be f of x minus g of x. But then you would add on the integral from 1 to 4 of, well, this time it's going to be g of x minus f of x. So again, the thing to point out is, for this formula, you need that f is always bigger than g. Okay, so to integrate this stuff, I'm going to simplify the integrals. So from -1 to +1. Okay, f of x minus g of x. That's x plus 1 minus 2x. I'll just simplify that up here. That is negative x plus 1. And then the integral from 1 to 4 is, okay, g of x minus f of x. You got to be careful here when you subtract off the function because you're subtracting x and you're subtracting 1. That's 2x minus x, which is x, and then minus 1. And it'll be that, these two things differ by a negative, and they do. If you multiply this by -1, you get negative x plus 1, which is equal to this. We now need an antiderivative. So for negative x plus 1, that's negative x squared over 2. And for 1, that is x. And we're going from -1 to +1. And we're adding to that the antiderivative for x squared minus 1, which is very similar. It's x squared over 2, but then minus x. And this goes from 1 to 4. I'm going to go to my calculator to get these values. For this first part, I got the number 2. And then for this second one, I got the number 4.5. And if you add those together, you get 6.5. That's acceptable. You could write this as a fraction, which would be 13 halves. So either of those answers will work for this problem. To solve this definite integral, we need an antiderivative. So for 3x squared, that's x cubed. For 2x, that's x squared. And for 1, we get x. And this is going from 0 to 1. If you put in the upper bound of 1, you get 3. If you put in the lower bound of 0, you get 0. And that makes the answer to this problem simply 3. Okay, the antiderivative for this is going to be both sine and cosine. Got to be careful. With sine, the antiderivative is negative cosine. And for cosine, the antiderivative is positive sine. And this goes from 0 to pi over 2. Maybe I'll carefully plug in the bounds. So negative cosine of pi over 2 plus sine of pi over 2 minus negative cosine of 0 plus sine of 0. Cosine of pi over 2 is 0, so negative 0 is simply, I'll just put 0. And then you have plus sine of pi over 2. Sine of pi over 2 is 1, so here's the upper bound stuff. And then, okay, what do we have here? Cosine of 0 is 1, so this is really negative 1. I'll put negative 1 here. And sine of 0 is 0. This is equal to 1 minus a negative 1. That's really 1 plus 1. And the answer to this is 2. All right, taking derivatives, we want to know what is dy dx, or if you'd like, you could just put y prime. Both are fine. Okay, so for this one, 5x to the power of 6, that is 30x to the 5th minus 4 plus 3e to the x. And I'll put plus 0 here. You don't have to include that if you don't want to, but that is it for this problem. This is the derivative of that function. For this whole question, you don't have to simplify your answers. You can just simply differentiate and be done. Let's see, for this problem, this is definitely a chain rule question because we have compositions. But just to be careful, to rewrite the original function, cosine squared means you're taking the cosine of 5x plus 1, you're taking that whole function and you're squaring it. We're going to have to use the chain rule twice because here's our first composition, it's something squared, and our second composition comes from this 5x plus 1. So if you want to find y prime, you'd start by pretending that this is just x squared. I mean, it's not, but you bring down the 2, you copy down all the stuff on the inside, and then you subtract 1 from the exponent. The chain rule says you now have to multiply by the derivative of all of the stuff that was composed in this first function. So that's really cosine, and the derivative of cosine is negative sine. It's negative sine of 5x plus 1. But again, we're, got to take the derivative of this whole thing. By the chain rule, since we have 5x plus 1 and not just x, I have to multiply by the derivative of that thing, which is 5. So this negative sine of 5x came from this first part, and this 5 came from the next part, which is this thing here. So don't have to simplify it. This is the answer. For this question, I see we have a product of two functions. So I'm thinking product rule. This is, x to the 1/2. I'll rewrite that. And then we have tangent of, well, we actually have a composition. So we got to be careful here. We'll have to use the chain rule when dealing with this part. So the first thing I notice is we have a product of two functions, x to the 1/2, as well as this part here. The product rule says you take the derivative of the first and then simply copy down the second. But then you add on the second times the derivative, you add on the first times the derivative of the second. The derivative of the second, it's secant squared of pi x, but because that wasn't just x, it was pi x, you have to multiply by the derivative of pi x, which is pi. Here's the answer. Here we have a fraction, a quotient, so I'm thinking quotient rule. To find the derivative, it is the derivative of the top times the bottom minus the top times the derivative of the bottom all over the denominator, the bottom, squared. You could simplify this, but this is the answer. Okay, here we again have a composition. So I see that 1 minus x is composed into the arctangent function. If you'd like, you can also think of this as tangent inverse of 1 minus x. Either is okay. The rule that we had for arctangent is it's 1 over 1 plus whatever's inside the function squared, which is 1 minus x. But by the chain rule, you have to multiply by the derivative of 1 minus x, which is negative 1. I'll leave the answer like this, and that's it. Another composition. 1 plus x squared is composed in the natural log function. The rule for the natural log was 1 over whatever is inside that function, which is 1 plus x squared. And by the chain rule, you have to multiply by the derivative of 1 plus x squared, which is 2x. More compositions of functions. I really am viewing this as something to the 7th power. So if you take the derivative of that, you bring down the 7, you copy down the inside part, you subtract 1 from the exponent. And by the chain rule, you have to multiply by the derivative of 2 to the x plus 1. The 1 goes to 0, but 2 to the x, it's almost equal to its own derivative, but you have to multiply by the natural log of the base, which is the natural log of 2. And this is the answer. Y is equal to x to the 2x. There's a little bit of a trick for this problem. We don't really have a rule that works nicely for this because we have both variables in the base and within the exponent. So you can't just like bring the 2x down front and subtract 1, or you can't say the derivative is e to the 2x times the natural log of x. That doesn't make sense. The idea for this one is you start by taking the natural log of both sides of your equation. And you're going to take the derivative of this new thing by using implicit differentiation. So that is, if you take the derivative of the left, the derivative for the natural log is 1 over what's inside the function, but you have to multiply by the derivative of what's inside the function, but that's simply y prime. On the other side, well, I left this part out, but technically you're supposed to rewrite this side. You can bring this 2x to the front of the log function. This is a property that logarithms have. If you have something to a power, a log means you can bring that power down front. So the right side is really equal to 2x times the natural log of x. It's this thing that we're going to take the derivative of, not this. I have to use the product rule. The derivative of 2x is 2, and then you just copy down the second. You then add on, leave the first thing alone, but then take the derivative of the second. So again, where this came from was the product rule. We had a first thing times a second thing. So we're pretty close. The goal is to solve for y prime. To get this by itself, you can multiply y to the other side of the equation. And that's exactly what my next step is going to be. Y prime is equal to y all times 2, the natural log of x, plus 2. Actually, I'm just going to leave it as 2. I know this x and that x cancel. I want my final answer completely in terms of x, but we're basically there. Y is equal to x to the 2x. So I'll record my answer as y prime is equal to x to the 2x times 2 the natural log of x plus 2, and that is the final answer. Question 4 is a related rates problem. So we have 2 cars. One, car A, is traveling east at 50 miles an hour. And car B is traveling north. It's going faster at 75 miles an hour. How fast is the distance between these 2 cars changing after 2 hours? So what we're asking about is, if I draw a line connecting, a straight line connecting the 2 cars, how fast is this line changing? I'm going to label some things in this picture. I'll call this side A for car A, this side B for car B, and then C is going to be the length of the line between the 2 cars. So as this moves and this moves, the length of this line is changing. It is increasing. Well, how fast is it increasing? What we're looking for when we solve this problem is, what is the rate that C changes with respect to time? We don't know this. Now, we do know a couple of things. We do know that the derivative of A with respect to t is 50 because we're told this value here. This is changing at a constant rate. It is increasing, which is why it's positive. Likewise, we also know dB dt. That is equal to 75. That came from here. A positive 75. If something is increasing in length, we'll assign it a positive value for its derivative. So I don't know this, but I do know these 2 things. The second step is to come up with an equation that connects all the variables. We will then take the derivative of that equation. Well, this is a right triangle. So therefore, the equation that we're going to use is a squared plus b squared is equal to c squared. we will differentiate this equation with respect to t. On the left, we get 2a times times dA dt. Why this happened is we brought down the 2, we copied down the a and raised it to the first power, but by the chain rule, since this isn't t, it's a different variable, you have to multiply by the derivative of this thing with respect to t. The same thing happens for b squared. It's 2b times db dt. Same thing on the other side. It's 2c times dc dt. Okay, we can cancel the 2 from both sides of the equation. This is the thing we want to know. And if we know everything else on this side of the equation, we'll just plug it in and get our answer. But there is an issue. I don't see A, B, or C stated within this problem. The only other thing we haven't used is this thing here, this after 2 hours thing. This is t is equal to 2 hours. But you can use this to find A and B. So by that I mean, if this car is going 50 miles an hour, after 2 hours, this will have gone how many miles? 100. So at this moment in time, A is equal to 100. Okay, B. B is going in this direction, and it is traveling 75 miles an hour. So in 2 hours, this will be 150. So great. I know A. I know B. I still don't know C. That's the only other thing I need to find. Well, by the Pythagorean Theorem, this thing right here, I'm going to put 100 in place of A, 150 in place of B, and solve for C. C is equal to the square root of 100 squared plus 150 squared. I'm not so sure this is going to come out to a nice number, but I have my calculator here. So that's the square root of 100 squared plus 150 squared. It's not perfect. I'll round it to 1 decimal. I think this will be good enough. That is 180.3. That is the length of C. I'm going to put all this information into this equation. The only thing I won't know is dc dt, and we can solve for it. So what I'm going to do is divide both sides by C. So like this whole side will be divided by C. dc dt is equal to A times dA dt plus B times dB dt, all divided by C. If I plug in all these numbers, again, A was 100, dA dt was 50, B was 150, dB dt was 75. C, it's roughly 180.3. If I type all this into my calculator, I'll have my final answer. So let me do that now. Let's see. Again, that was 100 times 50 plus 150 times 75, all divided by 180.3. Roughly, the answer is 90.1. And 90.1 what? Miles per hour. So I'll put miles per hour. This thing here is the final answer. All right, finding limits by using L'Hopital's rule. For L'Hopital's rule, what we're looking for is something of the form 0 over 0 or infinity over infinity. So we can determine this by plugging the number 0 into all of the x's. It's a good starting point for any limit anyways, because if you get a number back, that might actually be the answer to the limit. However, 0 times sine of 0 all divided by 1 minus cosine of 0 is, well, that's 0 in the numerator. Cosine of 0 is 1. This is 0 over 0. That is an indeterminate form. It just means you can't solve the limit this way. But in this particular case, L'Hopital's rule says you can take the derivative of both the top and the bottom, and that will be the new limit to consider. For the top, I have to use the product rule. The derivative of the first is 1, and we leave sine of x alone. We then add on, leaving x alone, but multiplying by the derivative of sine, which is cosine. The denominator, the derivative of cosine is negative sine, so we have negative sine. But, those negatives will cancel, and our limit is really, the limit as x approaches 0 of sine of x plus x cosine x all over sine of x. This is another indeterminate form. If you put 0 in place of the denominator, well, sine of 0 is 0. But this is 0, and 0 times whatever this is 0 as well. So we actually have another 0 over 0. But that's okay. You can use L'Hopital's rule as many times as you need. So let's go again. This is the limit as x approaches 0 of, okay, in the numerator. The derivative of sine of x is cosine of x. And then we have to use the product rule on this part. So the derivative of x is 1, and then you just copy down the cosine of x. You then add on x times the derivative of cosine, which is negative sine. And for the denominator, when we take the derivative of that, the derivative of sine is cosine. Okay, can we just, there's really not much to simplify. Well, I guess we can add those two. Yeah, why not? Let's simplify this a little bit. This is the limit as x goes to 0 of. The numerator is, well, that's really 2 cosine of x minus x sine of x. And the denominator is cosine. This is no longer an indeterminate form. We can just put 0 into all the x's. When you do, you get 2 minus 0 over 1. And that means the answer for this problem is 2. Okay, do we have another L'Hopital's rule situation here? This is the natural log of 1 over 1 minus 1. The natural log of 1 is 0, 1 minus 1 is 0, so certainly, L'Hopital's rule. We didn't actually figure out the limit, but we can take the derivative of both the numerator and the denominator. The derivative of the numerator is 1 over x, and the derivative of the denominator is just 1, or if you want, 1 minus 0. If you simplify this thing, oh, well, I don't even need the denominator anymore. It's just 1. I'm left with 1 over x. If I put 1 in place of x, I get my answer for the limit, which is equal to 1. What are the critical points for the function f of x? To find those, what you do is you take the derivative, and you determine where it both doesn't exist and where it's equal to 0. The derivative is 4x cubed minus 12x squared. This exists everywhere, which means I'm only going to check to see where it's equal to 0. Where is 4x cubed minus 12x squared equal to 0? Well, I see I can factor out a 4x squared, and left over is x minus 3. Checking to see where this is equal to 0 is a matter of putting both factors equal to 0. Where is 4x squared 0? And where is x minus 3 0? 2 places, 0 and 3. These are the 2 critical points for this function. Now, it so happened that for this given interval here, both of the critical points fell within the interval. That might not always happen, but it did here. That is important because if you want to find the global min and max of the original function, what you do is, for your original function f of x, not the derivative, you check the endpoints and all of the critical points that fall within the interval. Between these 4 numbers, there's going to be a biggest and a smallest. That is the location of your global min and your global max, respectively. So here I'm just, typing in my function into a calculator, the original function, and I'm going to my table and entering in these 4 numbers. And the values I'm getting back are 5, 0, negative 27, and 125. This is the global min. It's the smallest of the 4. And this is the global max, which appeared at an endpoint. Those are the 2 answers for this problem. Okay, so the indefinite integral for this is going to be 2x to the 5th over 5 minus 3x squared over 2, and then plus 2x plus c. Nothing really simplifies, so this is my answer. For this integral, I see I have a product. You can't just integrate both things separately. In fact, maybe I'll just write this down as a note. Are you allowed to just take the integral of both pieces separately? And then that's your answer. And the answer to that is no, this is no good. Like, you can't do that. But what you can do is take this x and distribute it into the parentheses. So we're changing the problem so it looks like this. It's the integral of x times the square root of x plus x. And furthermore, x times the square root of x, I'm going to rewrite that as well. That is the integral of x times x to the 1/2 plus x. I'm doing that because we can rewrite x times x to the 1/2 as x to the 3/2 if you add the two exponents together. You add the 1 and the 2, 1.5 is 3/2. Written this way, changing the problem from a product to a sum of single terms, we can find the antiderivative. It is x to the 5/2 divided by 5/2 plus x squared over 2. Sure, you can simplify this. I'm just going to leave it alone and say that this is the final answer. I'm going to rewrite this one a little bit. This is really the integral of 3 over 1 plus x squared plus the integral of secant squared. And also, I see I have this 3 here. You can remove that from the integral. This is 3 times the integral of 1 over 1 plus x squared plus the integral of secant squared. The reason I'm doing this is because when your function becomes complicated, you're allowed to split it up to think about smaller pieces. You don't have to do this for this problem, but I just figured I'd write it out this way. The integral of 1 over 1 plus x squared is what we call arctangent, which I'll use tangent inverse. The integral of secant squared is tangent of x, so not tangent inverse, but just tangent. And I'll add on my constant of integration, and I have my answer. So for this problem, are you allowed to say, oh, I have a fraction, so I'll just integrate the top, and I'll integrate the bottom, and then I'll be done? Can you just do this? And the answer is no. No. You can't do that. That's no good. What you can do is rewrite the integral in a way so you can integrate it. I can split this into 3 fractions. It's 4 over x squared minus x over x squared minus x to the 5th over x squared. And we can simplify this even further. This is really 4 times x to the negative 2 minus, I'll put 1 over x, and then minus x cubed. Written this way, the antiderivative is 4x to the negative 1 over negative 1 minus the natural log of the absolute value of x minus x to the 4th over 4 plus c. And this is the final answer.